Hello everyone, and in this video we are going to be walking through the entire process of training a machine learning model from scratch. And to be specific, what we're going to be doing is training a linear regression model so that we can predict housing prices. And so the housing price will be what we refer to as the target, and we're going to be making use of features. These are the inputs that our model will take in order to make a prediction. And these features are going to be things like the house's age, the population, number of rooms, etc. So another thing to note is that in the realm of machine learning, this is specifically called supervised machine learning. And we're going to be making use of a labeled data set. And what that means is that every single one of our data points in our data set has a label which says, I know exactly what the value of this house is. So we have housing market data, and I know for sure that, this house sold for $300,000, and that tells me and the model during its training process, what the real value is, so that it knows how to tune its parameters when it's trying to come up with the best way to make its predictions. And I just want to give credit to the author, Aurélien Geron, and there's a link to his book here. This is adapted from his work, and it's using the housing data set that is public in his GitHub account. So just want to give a shout out to that before I get too deep into this. And so the very first thing we're going to do here, and you guys will have this whole code, so I'm just going to walk through what it does. But basically, making all my imports for NumPy, Pandas, scikit-learn, and we're going to be downloading this actual housing file, and we're going to be basically putting it into a Pandas data frame so we can work with it in Python. And before we really do anything too fancy, we're just going to plot the histogram of stuff so we can see what this data looks like, and also the types of columns that we're having inside of this data set. So in our case, we're going to be looking at longitude, latitude, median age, total rooms, bedrooms, population, households, income, median house values, ocean proximity, income category. And so the key thing to note, and this is the output of running housing.info, so a dataframe.info will tell us exactly, how many rows do we have populated here of non-null values, as well as a data type. And so one thing to call out is that ocean proximity is an object. So this is a categorical variable, and unlike the other ones, it's not numeric. So when it comes time to actually training our model, we're gonna have to do some processing, some pre-processing with that in order to handle those. So we're gonna get to that in a moment. And another thing I wanna call out is the fact that if you look at total bedrooms, you can see that every other column here has 20,640, but this one is missing some data. And so in the real world, you're gonna have an imperfect data set, and we have to figure out how do we handle missing pieces of information, and how that will impact training your models. So that's going to be involving our cleaning process, and we're going to get to that as well. So this also is just a histogram of what we're looking at. So you can see this housing data specifically is of California, so you can see how there's like clusters of houses in specific areas. This is probably like North Bay NorCal and SoCal. And you can also see how on some of these plots, you're not seeing like a perfect distribution in terms of a Gaussian curve, so to speak. Ideally, it would be symmetric. But what you're seeing is it's skewed right, which means that we have more data points kind of pushing this thing off to the right a bit, which are not ideal for what we want in terms of having an optimized training process. And then in addition to that, we can see that like for housing median age and housing value, these are things also where we've got this thing called capping that's happening. And capping is something specifically that we do when we want to limit the effect of outliers on our data sets, because if Bill Gates or Warren Buffett or some rich guy basically buys a house that is astronomically high, and it goes into our data set, it can basically blow up our training process and make the performance of our model weaker at the end of the day. So that's the purpose of capping, and that's why you see these things right here. And so, but as you get into this, the very first thing to think about is when you train a model, the goal is to take data and make predictions with it. And so you need to have some kind of training set up for it. So we have to break our data set, our entire data set, into a training set and a test set. And so the test set will be what will evaluate our model on. So we're going to train our model, and then we're going to ask our trained model to make predictions, and then we'll compare those predictions with our test set to see how good they are to the actual values they are. And this is something that is very important and a critical process involving making sure that you have an accurate representation between your training set and your test set. And basically it's polling in essence. And you want to make sure that, when you have, especially not with big data sets, when you have a smaller data set, how do you make sure that your training set is sufficiently representative of your test set and vice versa? And so when it comes to us predicting housing prices, something else to note is that your training data set, we're going to purposefully take out the house value, our target variable, from it because we don't want to have overfitting. And so we have to kind of and this is where the art kind of comes into this whole process. You just have to know, or you'll be told that when you are doing your sampling and you're breaking your training set into a test set and a train set, that you're going to want to make sure that how can you make sure that you've got an accurate representation of each other? In our case, we're going to base this on the income of people because we think that income of the person is going to have a pretty strong correlation to the price of the house that they're living in. And so what's happening here in box 59 is we're doing this thing called stratified sampling. And the purpose of stratified sampling is it's going to, and this is all done through scikit-learn, is it's going to split our data set into a training set and a test set, and it's going to ensure that between these two data sets, they still have representativeness between each other. And specifically, the feature that we care about is that income of people, because we think that's probably one of the most important predictors of the value of the house that these people live in. And so when it comes to this part, it's one of our inputs to this stratified sampling method that we're calling. And just to plot this out so we can see it, we can see that our income categories are very representative of each other between our test set and our training set. And if you changed what you were stratifying your sampling on between your training and your test set, you're going to get a very different model. It's going to have different performance. And so, let's say you picked wrong or you picked something else, basically at the end of the day, numbers are going to govern how you act. And so as a machine learning engineer, it's really about trying to minimize the root mean squared error that your model has between its prediction and the true value. And that's something that you'll just learn through iterations and trying new stuff. But for the sake of having a walkthrough, this is what we have. So this graph's just to show that the stratified sampling that we did based on income does visually look like we still have the same distribution between our two data sets, which is good. And also in our case, the 0.2 refers to the fact that my test set will be 20% and my training set will be 80%. Sometimes it's a 90-10, but in general, your training set is going to be a lot bigger because you want to have a lot more practice problems, so to speak, for your model to learn on than your test set. Now, the next thing we're going to do also that we've split up our data set is we're going to drop our columns that refer to the house value because that's our target variable. And as we've said before, when we leave in the target variable inside of our training set, this causes problems because the model will overfit and it's going to memorize patterns. And so it's going to have a really great way of predicting, house prices inside of the training set. But when it comes to outside unknown data points, which is the entire point of us training a model, it's going to fail because it's going to basically fit, a ridiculous trend line or something to that data that is not going to help us. So we intentionally hide the correct answer, so to speak, from our model during the training process by just dropping the column in our training set. Next thing we have to do is we have to take care of missing data points inside of our training set. And in this case, noticing that we didn't have a complete record of total bedrooms. And so we're going to make use of something called imputing. And when we impute, basically what that means is we're going to take whatever is null and we're going to put in the median. Could also be the mean. You have different options to go with. But in our case, we're going to go with the median value. And so every time there's a null, we're just going to put in the median value and assume that, that would have been pretty close-ish to what the value was if it was there. And the reason why we're doing this is because it's not destructive in the sense that we're not going to be making our data set any smaller. Alternatively, what we could do is we could just delete any row where we didn't have complete records of everything, or delete a column where you didn't have 100% completeness of everything. But that's very destructive, and it can also that would have the impact of potentially hurting your model's performance at the end of the day. So we impute, again, using scikit-learn's built-in modules. And next here, we're going to have to handle our categorical attributes. And so, a category that might be important to a home buyer or in the market would be ocean proximity. And this is something that falls into a bucket like A, B, or C. In our case, it was like, near ocean, ocean within an hour, whatever. And so in our case, because you've got these categories, they are not numbers. They are just things. So you can't say or let, near ocean be 0, ocean within 20 minutes is 1, ocean within 30 minutes is 2, because then it'll mess it up. So what we have to do is a thing called encoding. And so we're going to make use of this, again, module called one-hot encoder. And one-hot encoder is basically going to come in, and for every single one of the categories that we have, it's going to create a new column. And that column is going to be a Boolean of true or false for whether or not a particular house is under that category. And by doing that, we are turning a category into a number or a Boolean, so to speak, so that our machine learning models can actually learn it and incorporate it into their thinking process, because otherwise they can't. They can only work with numbers, they can't work with categories, and that's why we need encoders as we are pre-processing our data for training. And then the other thing we can do is, again, clip our outliers. So if we have a situation where you do not want to let extreme house prices, in super wealthy neighborhoods blow up your training, because, you really care about predicting people who are kind of, the majority of your audience and not just super rich people or super poor people, perhaps. We're going to be using clipping to basically say, look, if your house sold for $800 billion, I'm just going to say that it sold for $500,000. So I'm keeping the data there, and I'm just going to, but I'm going to change its value to 500,000. So I have a limit on the value, so it's not going to hurt my averages too much. And so that's what we're doing at this step. And again, just plotting this out so we can see what's happening in our histograms. Again, I want to call out the fact that we don't have perfect Gaussians. So our total rooms, for instance, is skewed right, because you can see it's got a fat right tail to it compared to the left tail on the Gaussian, or this bell curve. So what we're going to do is we're going to make use of log transformations, and log transformations will help us get a more bell-shaped curve for these data points. And then in addition to that, they'll make the numbers a bit smaller, which can help us with the training process. So after doing the logs, you can see that these are now much more Gaussian-like, which is what we want. And as we continue, we're going to make use of this thing called scaling. And the purpose of scaling, again, all this stuff just has to do with optimizing our training process, is going to have to do with taking it. So if right now we were to look at households, and this is the log of households, not households anymore. It's at 6, but that appears to be the center of your Gaussian, which is the average, and 1 standard deviation. So after we scale our data, what's going to happen is it's now going to have its average will be at 0, and then every standard deviation will be 1. So any data point here, that means above this, means that it's more than 2 standard deviations above the average of the population. And again, this scaling stuff is just helping with training our process, because we're going to be trying to fit a linear regression model to this so that we can make predictions on the housing prices. Now what we're going to do is we're going to take our data set that we've done our scaling and our log transforms to, and our cleaning, our imputing, and we're going to fit a linear regression model to it. And before we do that, though, we are going to drop again our house value, because we don't want that to be causing overfitting during our training process. So we just run through all this. And then what happens next is we take our model that we've trained and we're going to have it make predictions. And so basically when it makes the predictions, we're going to take our test set and we're going to hide the true values from it. And we're going to feed those values to our model. And we're going to say, based on these features, what do you think the target is? What do you think the house's price is? And so, and we'll know the true price, and then we'll basically just compare the true price with the predicted price. And so once we've done that enough times, we'll have a bunch of errors. Error is the difference between the prediction and the true price. And because we just want to look at an absolute value, we take the root mean square of that difference, because it could be positive or negative. And so that's what we care about. So, when it comes to, this is empirically measuring the performance of our model. Ideally, you have the smallest RMSE you can, because the RMSE is basically how bad was your prediction. So if your RMSE was 0, that means you had a perfect prediction. If your RSME was 34,595, in our case, what that means is that was on average, our model was off by $34,595. So that's how off our guesstimate was for what this house's price should be. And just to visualize this a bit more and show how our model performs over the different house prices, this is what we have. So the way to interpret this again is, this is the true value, this is the prediction. So in the best case scenario, our true value fell on the same line as our prediction, which means it was on this red dashed diagonal line right here, y equals x. So in all these examples, we had a perfect prediction. But anytime we're far away from this line, it means that our true value did not match up with this prediction. And so what we're seeing is that we have a curve in this data. And, for the sake of lack of compute resources and time, we're trying to make use of a linear model to predict potentially very complex relationships between housing prices and all of our features in our data set. So, what this is telling us is that, it's okay, and we at least have a baseline, but, for other houses, to have a better prediction of performance, we should be looking into a few things. So there's a bunch of different models out there we can go with. In this case, we just went with linear regression, but there's random forest, there's gradient boosting machines, there's neural networks, there's many other alternatives out there. They just take a lot more compute and time. They also have more hyperparameters to be tuned. So again, more time and resources are going to go into tuning those parameters, but the benefit would be that you could be more confident in your predictions of the model that you have. Another thing that we can make use of is, even for a linear regression model, we can tune the hyperparameters of this. And in our case, we can see that, we could have forced a particular y-intercept of our prediction, and that would have helped with lower value houses. So, it really depends on and this will be told to you from your manager, but basically, what range of value of houses do you care about being able to predict? Like, are we trying to target middle class families, lower class, upper class, whatever? And so, in our case, we can say that, for houses that are in the $200,000 to $300,000 range, our model looks like it's pretty good. But as soon as houses fall, around 100,000, especially below 100,000, our predictions start becoming farther and farther off. Same thing goes for here. Once we start getting out to the 500,000 area mark, our predictions just aren't that great. So our confidence becomes less and less in the predictions that we're making based on the model that we have. So again, we can turn to different models to try to help with this. Another thing we can do to improve performance is to go back to the data set we originally had and try to see if there's additional features that we can, transform. For example, we can look at the population and the number of houses. So potentially there's some interesting insight to be found from how many houses are available, like the population density per house, how many people are competing over the same house. Maybe that has an impact on the price, or how many rooms are in a given house. So there's, if you look at these ratios and you think they might have something to do with the ultimate value of the house, this is stuff you can add into your data set in your, pipeline to try to improve your model's performance. So this just gives you a baseline of how it all works in a very simplistic way. This is all open, so you guys can play around with it and start tuning it and trying different models. So I hope this is helpful stuff. Thank you all for watching. Let me know if you have any questions, and be well.